Welcome back to the deep dive. Today, we are grabbing a shovel, but I want to be very clear right off the bat. We are not planting petunias.
No.
We aren't talking about which mulch color pops against your siding, and we definitely aren't discussing curb appeal.
Absolutely not. In fact, if you're worried about curb appeal, you're looking at the wrong part of the house. We are going way, way below the surface today.
Exactly. We are conducting a forensic investigation because, let's be honest, there is a specific sinking feeling that every homeowner knows. You spend a fortune on a new patio or a retaining wall or maybe just the foundation of the house itself. You write the check, the crew leaves, it looks beautiful, and then maybe 2 years later, you see it.
The crack.
The ominous, jagged line running right through your expensive stamped concrete.
Yeah.
Or you walk into the backyard after a heavy Tuesday rainstorm, and it's not a yard anymore. It's a wetland. It's a swamp.
Oh, yeah.
You sink up to your ankles in mud that smells like despair.
That is the classic money pit scenario. It's
Yeah.
that exact moment you realize your asset is actually a liability.
It is. And the immediate reaction, I know I've done this, is to blame luck. You say, oh, I just had bad luck with the weather, or that contractor must have been having a bad day.
Right. It's always someone else's fault or just random chance.
And sure, maybe the contractor wasn't great. But what we're digging into today, based on this massive stack of geotechnical reports, soil surveys, and engineering manuals you've brought, is that luck has almost nothing to do with it.
It's almost never luck. Luck implies randomness. What we are seeing in these failures is, well, it's inevitable. It's predictable.
It's physics.
It is math, physics, and chemistry. When a landscape project fails, when that concrete snaps or the yard floods, it's usually because we ignored the invisible forces underground.
So all the stuff we can't see.
All the stuff that actually matters. We're talking about soil mechanics, hydraulic conductivity, and chemical reactivity.
Okay, hydraulic conductivity is already sounding like we're back in a university lecture hall. But the mission today is to make this usable. We want to understand why things fail so we can build things that actually last 50 years instead of 5.
Exactly.
Because frankly, I'm tired of fixing the same fence post every 3 springs.
Precisely. And to do that, we have to look at the ultimate stress test environment. A lot of the research and case studies we are covering today focus on one specific place.
Texas.
Texas.
Yeah, I saw that in the notes. Why Texas specifically? Is it just because everything is bigger there, including the repair bills?
Well, sort of. That's part of it. But Texas is fascinating from a geological perspective because it's a convergence zone. It's where several massive ecological and geological systems collide.
A convergence zone, okay.
You have the humid subtropical climate coming in from the southeast. Think swampy, wet heat, like Houston.
Got it. Oppressive humidity.
Then you have the arid desert pushing in from the southwest, from El Paso.
Total opposite.
Complete opposite. And then you have the temperate prairies coming down from the north, from the Great Plains.
So it's a weather battleground.
And a soil battleground. There are over 1,300 classified soil series in Texas alone.
1,300?
1,300. It has more soil diversity than almost any other state. But the key takeaway for the listener, whether you live in Dallas or Detroit or Dublin, is that Texas represents the extreme.
It's the worst case scenario.
It's the perfect storm. If you can understand how to keep a foundation stable in the Blackland Prairie of Texas, you can build a resilient yard pretty much anywhere on Earth.
It's the boot camp for landscape engineering.
It is.
If your wall can survive a Texas summer and a Texas flood, it's bulletproof.
It really is.
All right, let's get our hands dirty. We have to start with the dirt itself. And there is a term that keeps popping up in these documents. It sounds like a soup recipe or maybe a blues band, but apparently it's a nightmare for homeowners.
Black gumbo.
Black gumbo. It sounds harmless, doesn't it? Almost friendly. It sounds delicious, but based on the photos in this report, it looks like it eats houses for breakfast. What is it, and why is it so destructive?
So black gumbo is the colloquial term for a specific type of soil, technically known as a vertizole.
A vertizole?
And specifically the Houston Black Series, which is a bit ironic because it's found all over central Texas, not just Houston. If you look at the soil maps, this stuff runs in a massive band right down the middle of the state through Dallas, Austin, San Antonio. It's the spine of the state.
Okay, but plenty of places have clay. I have clay in my yard. It gets hard in the summer. It's sticky when it's wet. Why is this stuff special?
That's the key question. The reason it's notorious is due to its mineral makeup. It's all about what it's made of at a microscopic level. It contains a very high percentage of smectite clay.
Smectite. That sounds like a comic book villain substance. Beware the smectite.
It acts like one. To understand why, you have to visualize the microscopic structure. Think of smectite clay particles like a deck of playing cards.
Okay,
When the soil is dry, those cards are stacked tight together. It's a dense, hard brick. You can barely get a shovel into it.
Right, I've seen that. The ground gets like concrete in August.
Exactly. Now imagine if you poured water onto that deck of cards. In a normal, say, sandy soil, the water might flow around the deck. But in smectite, the chemical bond between the cards is really weak. The water molecules don't just go around it, they actually rush in between the individual cards in the deck.
So it pushes the cards apart from the inside out.
Violently. It pushes the layers apart at a molecular level. The crystalline lattice expands. This isn't just a little fluffing up like a sponge you'd use in your kitchen. We are talking about massive volume change.
How massive? Like 10% bigger, 20?
It can be more than that. The volume can swell by a huge factor. This is what we call shrink-swell potential.
So when it rains, the ground isn't just getting wet, it's physically getting bigger. It's trying to occupy more space.
Significantly more space. And conversely, when it dries out, all that water leaves, and it shrinks back down. The source material notes that in dry spells, you can see cracks in this soil that are up to 4 inches wide.
4 inches? You could lose a shoe in that. That's an ankle break.
Oh, it's worse than that. It's much worse. The cracks can go 6 feet deep.
No, 6 feet.
6 feet.
Wait, I'm trying to visualize that. That's deep enough to bury a person. If I'm walking through a field in a dry Texas summer, am I literally going to see these fissures opening up into the abyss?
Absolutely. In fact, ranchers in the Blackland Prairie have historically lost livestock in them.
You're kidding?
Not at all.
Yeah.
Calves break their legs. Tools get dropped down there, and they are gone forever. And when you look down into them, you aren't seeing rock. You are seeing the raw, dry, blocky structure of the clay. It looks like a giant jigsaw puzzle that's been pulled apart.
That is genuinely terrifying. But okay, a hole in the ground is one thing. I could fill a hole. The real problem is when it closes back up, right?
Right. Exactly. The shrinkage is the setup. The swelling is the punch. The problem is the pressure. When the drought ends and the rain comes, water fills those 6-foot chasms. The clay absorbs it. The deck of cards expands. The cracks slam shut. And then the soil keeps expanding.
And it has nowhere to go.
Nowhere to go but up and out.
And if my house is sitting on top of it...
That lifts the house.
Yeah.
We're talking about swelling pressures that can reach thousands of pounds per square inch. PSI.
Thousands of PSI. Contextualize that for me. Are we talking about lifting a car?
We are talking about enough force to snap a reinforced concrete-grade beam like a twig. It's not a gentle lift. It can lift a slab foundation several inches. And the real killer is that it never, ever happens evenly.
Right, because the north side of my house might be in the shade and stay wet, while the south side is baking in the sun and drying out.
Exactly. That's differential movement. One side lifts, the other side drops. The house twists. Drywall cracks. Door frames go out of square. Windows shatter. You can't close your doors anymore.
I've heard people talk about that. Their doors stick in the summer.
That's the house moving. The documents actually mention a phenomenon called Gilgai relief.
Gilgai? That sounds Australian.
It is. It's an Aboriginal word. It refers to these micro highs and micro lows on the surface of the land. It's a very subtle, wavy pattern.
So the ground itself is lumpy.
Exactly. Because this soil swells and shrinks so violently over centuries, the ground literally churns itself. It becomes wavy. The high spots are where it swelled more, the low spots where it swelled less.
So the ground is boiling, just in really, really slow motion.
That's a great way to put it. It's a slow motion boil. And if you try to put a flat, rigid piece of concrete like a patio or a driveway on top of a wavy, churning ocean of dirt, you're going to lose. The concrete will always lose.
Okay, so we have this living, breathing, heaving clay. My instinct as a skeptical homeowner who likes to feel in control is to fight it. I want to beat it into submission. If I'm building a patio, I'm going to rent the biggest plate compactor the rental shop has. I'm going to pack that dirt down until it's harder than the concrete I'm pouring. That seems like the logical move to stop it from moving.
It feels logical, doesn't it? If I make it hard, it won't move. But this brings us to one of the biggest misconceptions in landscape construction. The myth that maximum compaction is always good.
Is compaction bad? I thought we needed a solid base. Every manual says compact the subgrade.
We want a stable base,
Yeah.
but there's a very, very fine line between structural compaction and overcompaction that kills the soil's functionality. It's a double-edged sword.
Okay.
We have to look at a concept called the Proctor density.
Proctor density. That sounds like a medical exam I don't want to take. Unpack that for us.
It's the standard engineering test to determine the optimal moisture and density for a soil type. Basically, you take a sample of soil in a lab, put it in a mold, and drop a calibrated hammer on it repeatedly.
You just hit it with a hammer.
A very specific hammer, a very specific number of times. You do this at different moisture levels to find the sweet spot where the soil packs together the best.
Okay, so you find the sweet spot and you tell the contractor, hit this number.
Right. Usually for a building pad or a road, you want 95% or 98% of that standard Proctor density. You want it tight. But here is the catch. If you compact clay too much, if you go way past that standard, you are essentially turning that soil into a brick.
Which is great for supporting a house, isn't it?
It's good for load bearing, sure. It won't settle. But it's terrible for everything else. You've destroyed its other functions.
What other functions? It's just dirt.
Well, for one, life. The source data shows that root growth is severely affected at certain bulk densities. For clay, if you get above 1.4 grams per cubic centimeter, roots physically cannot penetrate.
So you're strangling your plants from below. You plant a tree, and the roots hit this compacted floor and just spin in circles.
Exactly. They get root bound in the ground. They can't access water. They can't access nutrients. But worse, you're creating an impermeable layer.
Impermeable, meaning water can't get through.
At all. We'll talk more about water in a minute. But if you overcompact the soil under your lawn, the water can't go down. It just sits there. You've created a parking lot, painted it green, and then you wonder why the grass dies every July.
That explains so much. I've definitely had patches of yard that just refuse to grow anything no matter how much water I dump on them. I thought the soil was just bad.
It's not bad. It's choked. And ironically, by dumping water on them, you might be making it worse.
Yeah.
But there was a really interesting, slightly terrifying example of compaction in the notes regarding the Houston area and NASA.
Oh, this is the subsidence story.
Yes.
This blew my mind. We're talking about the ground literally sinking, right? Not just one house, but the whole area.
Yes. This is the Houston District case study.
Yeah.
So historically, Houston relied heavily on groundwater. For decades, they were pumping massive amounts of water out of the aquifers beneath the city to supply the population and industry.
Creating a void, like sucking a milkshake dry.
Not a void like a cave, but they're reducing the pressure.
Mm-hmm.
Think of the clay layers deep underground like a sponge that is soaked in water. The water pressure, what we call artesian pressure, helps hold the sponge open. It supports the weight of the earth above it.
Okay. It's like a hydraulic jack holding everything up.
A perfect analogy. When they pumped the water out, that artesian pressure dropped, the internal support vanished, the hydraulic jack was gone.
And gravity took over.
The immense weight of the earth above crushed those clay layers down. It compacted them. And here's the scary part. It's inelastic deformation.
Meaning it doesn't bounce back? Ever.
It never bounces back. Even if you pump water back in, the structure is crushed. It's done. The land surface sank.
How fast did this happen?
In the NASA area, the source details mention that the maximum clay compaction occurred less than 6 months after the pressure declined. It happened fast.
So entire neighborhoods, infrastructure, the Johnson Space Center, everything just lowered.
By feet, not inches, feet. In some areas, over 10 feet.
10 feet.
And that changes everything for drainage. It changes flood risk. It changes where the coastline is. It highlights that soil isn't static. It's a mechanical system that responds to pressure and water. If you change the water, you change the shape of the ground.
Which is the perfect segue to Section 2. We know the soil moves. Now we need to talk about the trigger. Water. Hydrodynamics.
The science of moving water.
We've established that the soil is a loaded gun, but the water is the finger on the trigger. And there is a variable here that kept showing up in the engineering reports. KSAT, spelled K, subscript S-A-T.
KSAT. That stands for saturated hydraulic conductivity.
Which is a fancy way of saying,
how fast does water move through the soil when the soil is completely soaked? It's the speed limit of the dirt.
okay, give me the spectrum. I want to know the difference between a sandy beach and this black gumbo we've been fearing.
On the fast end, you have sand or gravel. The sources list sand as having very high conductivity. We're talking greater than 0.01 centimeters per second.
0.01 centimeters per second. That sounds incredibly slow. That's like watching paint dry.
In the world of soil physics, that is a Formula One race car. Water zips right through. It disappears instantly. If you pour a bucket of water on sand, it's gone.
Right. Okay. And on the other end, the clay.
Heavy clay. The conductivity can be as low as 0.0000146 centimeters per second.
That is, I can't even process that number. It's basically zero.
It's practically stopped. It's a traffic jam where no cars are moving. The report explicitly says that in these heavy clays, water doesn't drain in the traditional sense. It ponds. The soil acts like a paved surface.
This explains why after a heavy rain in some of these neighborhoods, the water just sits there for days. I always assumed it was because the yard wasn't sloped right.
The slope matters, but you're saying even if the slope is okay, the water physically cannot enter the ground.
Right. The ground has rejected the water. It's full. And this leads to one of the most common catastrophic mistakes homeowners make. We call it the perched water table trap. And I guarantee you know someone who has done this. I feel like I'm about to be attacked. I bet I've done this. Lay it out.
Here's the scenario. You buy a house on this heavy clay soil. The grass looks terrible because, as we discussed, roots hate compacted clay. You think, I need better dirt.
Of course, that's the first thing you'd think.
So you go to the garden center, or you call a landscape supply company, and you order 10 yards of premium sandy loam.
That sounds delicious. I'd order that. It's dark, it's fluffy, it smells like success.
It looks great. It feels great. You spread it out over your yard, maybe 4 inches thick. You rototill it in a little bit, maybe not deep enough. You plant new sod. You water it. You stand back and admire your beautiful green lawn.
What happens next?
And you have just built a swimming pool for your grass roots.
How? I put down good soil. I spent hundreds of dollars on that dirt.
You put a sponge on top of a dinner plate.
Ah, okay. I see where this is going.
The water flows through that sandy loam, quickly high KSAT. It rushes down through that 4 inches. Then it hits the clay subgrade underneath, super low KSAT. The water hits that clay and stops dead. It backs up.
It creates a false water table.
A perched water table. The water sits in that 4-inch layer of good soil you just added. The sand turns into soup. It loses all its load-bearing capacity. So you step on your lawn to admire your work, and you sink to your ankle in mud.
And meanwhile, underneath, the clay is drinking that water slowly.
Exactly. By keeping that top layer saturated, you are force-feeding water to the clay underneath. So the clay swells. You've created a mechanism to keep the clay permanently saturated and heaving, while the top layer is a muddy mess that breeds mosquitoes and rot. It's the worst of both worlds.
That is tragic. So simply adding good dirt isn't the fix. You're actually making it worse.
Not if you don't account for where the water goes when it hits the clay. You have to give it an exit. You can't just layer good on top of bad and hope they get along. They won't.
Now, to complicate things further, the sources mention something interesting about how water moves in clay. It's not always just a slow seepage. Sometimes it's preferential flow.
Yes. This is the nuance that drives engineers crazy. We just said clay is impermeable, right?
Right. The traffic jam, the dinner plate.
Except when it's cracked. Remember those 6-foot cracks from the dry season?
The calf breakers.
When the dry season ends and the first big rain hits, the water doesn't soak in evenly across the surface. It finds the path of least resistance. It rushes down those cracks. It rushes down old root channels, wormholes, decay paths. This is called macropore flow.
So it's like a subway system for water bypassing the surface traffic?
Basically. The source insight here is that hydraulic conductivity can change by 1 to 3 orders of magnitude just based on these cracks.
Orders of magnitude, so 10 times, 100 times, 1,000 times faster.
1,000 times faster. So you might think your soil is sealed, but suddenly water is attacking your foundation 6 feet underground because it found a shortcut.
That is terrifying. It's not just a sponge, it's a sponge with secret tunnels.
Which is why modeling this stuff is so hard and why eyeballing a drainage solution usually fails. You can't see the tunnels.
Okay, so we've got moving soil, we've got trapped water, we've got secret tunnels. Now let's add chemicals to the mix. Let's talk about chemical warfare.
This is where things get explosive. And sometimes, literally.
I saw the term sulfate trap in the notes. I know what sulfates are, generally like sulfur, rotten eggs, but why are they a trap for a landscape project?
To understand this, we have to look at how we typically try to fix clay. If you were building a road or a large driveway on clay, the standard engineering solution for decades has been lime stabilization.
Yeah, you see the trucks spreading the white powder before they pave a road? It looks like snow in July.
That's calcium oxide, quicklime. It's amazing stuff usually. You mix it with clay, it raises the pH to above 12, and it causes a pozzolanic reaction.
Pozzolanic.
Like volcanic ash. It basically turns the clay into a low-grade cement. It makes it hard, it makes it waterproof, and it stops it from swelling.
Sounds like the perfect solution. The silver bullet. Why aren't we doing this everywhere?
Using the perfect solution.
Yeah.
Unless the soil has sulfates.
Like gypsum?
Exactly. Gypsum is calcium sulfate. If you have sulfates in your soil and you add lime,
what happens?
You trigger a chemical nightmare. You create a mineral called etrinite and sometimes thaumasite.
Those sound like villains in a sci-fi movie. Lord Etrinite has destroyed the galaxy.
They act like it. When etrinite forms, it has a weird crystal structure that occupies a much, much larger volume than the original minerals.
Yeah.
It expands massive amounts. The sources describe it as a chemical explosion in slow motion.
You're kidding. So by trying to stabilize the soil with lime, by trying to do the right engineering thing, you actually cause it to heave even worse.
Much worse. You are essentially manufacturing a heaving agent in place. There's a famous case cited in the notes about State Highway 161 in Texas. They treated the subgrade with lime to stabilize it. Standard procedure. But the soil was rich in sulfates.
What happened to the highway? Did it just crack?
Speed bump ridges. The road literally buckled up into ridges because the soil underneath expanded chemically. It wasn't water causing the swell. It was the chemical reaction itself. They had to go back and completely rebuild it. There are examples in Las Vegas, too. It destroys pavements, it cracks foundations, it ruins lives.
So the lesson here is test your dirt.
Before you do anything, you absolutely must test for soluble sulfates before you let anyone mix lime into your ground. It's a simple test, but if you skip it, you might be setting off a slow-motion bomb under your driveway.
That is wild. Okay, so that's the soil attacking the stabilizer. What about the soil attacking our pipes? We have buried metal all over our yards, gas lines, water lines, those galvanized screw piles for decks that are so popular now.
Corrosion. This is a huge, huge issue in these soils. The documents break down the corrosion variables. It's not just about the soil being acidic. People think, oh, pH 7 is neutral, I'm safe. Not necessarily.
What are the variables then? What actually makes a pipe rust away?
There are 4 big ones: chloride content, moisture content, pH, and resistivity.
Chloride, like salt.
Yes, and it doesn't have to be near the ocean. Fertilizers, de-icing salts, natural mineral deposits, they all add chlorides. High chlorides lower the resistivity of the soil.
And resistivity is key.
It's a measure of how easily the soil conducts electricity.
Why does electricity matter for a water pipe? Is there a current running through the ground?
Because corrosion is an electrochemical process. Rust is basically a tiny battery reaction. If the soil conducts electricity well, which means it has low resistivity, the electrons can flow freely from your pipe into the soil. That means your metal rots faster.
So a low number for resistivity is bad.
Very bad. And moisture plays a huge role here too.
Makes sense. Water conducts electricity.
Exactly. The data shows that once moisture content goes above 17.5%, the chloride concentration becomes the dominant factor.
So if you have wet, salty soil,
you're in trouble. Let's look at the lifespan estimates from the charts. This part is sobering. If you have chart 1 conditions, the best case, dry, neutral soil, high resistivity, a galvanized steel pipe might last 120 years.
That's plenty. I'll be dead by then. The house will be a robot museum by then.
But if you have chart 2 conditions, the worst case, low pH, high moisture, high chlorides.
What's the lifespan?
That life expectancy drops to about 28 years.
Whoa, 28 years? That's a mortgage. That's not forever. That means if I buy a house built in the 90s, the pipes could be dissolving right now.
Exactly, and that's why you see materials changing. The source talks about polymer-coated corrugated steel pipe, or CSP. It's designed to resist pH as low as 2.1.
2.1? That's practically stomach acid.
It is. In these harsh soil environments, you can't just throw raw metal in the ground and hope for the best. You need barriers. You need chemistry on your side.
So we've terrified everyone. The soil is moving, the water is trapped, the chemicals are exploding, and the pipes are dissolving. It sounds like we should all just move to a houseboat.
It's a hostile environment, for sure.
Yeah.
But we can build in it. We just have to stop guessing and start engineering.
Let's pivot to the solution. Engineering the fix. How do we actually build in this stuff? Because people do it every day. There are successful projects.
We can outsmart the soil. One of the most ingenious structural solutions mentioned in the texts is the void form.
Void form? I saw this. It sounds high-tech, like something from a spaceship.
It's surprisingly low-tech in concept. It's basically a cardboard box.
Come on. You cannot be serious. We are building million-dollar homes on cardboard boxes.
We're building over cardboard boxes. Here's the idea. You know the soil is going to heave, right? We've established that. You know the Blackland Prairie is going to rise up 4 inches when it rains.
Right. We've accepted that. It's the enemy.
So the goal is to not let your foundation touch the dirt. You isolate it.
Oh.
You drill deep concrete piers that go way down to stable soil or bedrock. Those are your stilts. Then underneath your concrete beams in your slab, you place these carton forms, heavy-duty, wax-impregnated cardboard boxes.
Okay. But I'm pouring 50,000 pounds of wet concrete on top of them. Why don't they crush?
They are engineered with a honeycomb structure. They are incredibly strong vertically. They can hold the weight of the wet concrete and the workers walking on them. But they have a fatal weakness.
Water.
Moisture. Once the concrete cures and becomes self-supporting, so it's sitting on the piers, bridging in the gap ground, moisture attacks the cardboard. The wax breaks down. The cardboard rots away over a few months.
Leaving a void, an empty space.
Leaving an empty airspace, usually 4 to 8 inches, between the dirt and your house. So when that clay swells up, it just expands into the empty air. It pushes into the void. It doesn't hit the bottom of your house.
That is brilliant. You're giving the soil room to throw its tantrum without touching the furniture.
Exactly. It isolates the structure from the Earth's movement. It's the only way to guarantee stability in highly expansive soils. It's essentially a hover house.
But wait, isn't that expensive? I mean, custom cardboard deep piers? This sounds like it adds a lot to the cost of a build.
It adds cost, absolutely. But compare that to the cost of foundation repair 5 years later, which can be $50,000, $100,000, or the cost of windows that won't close, doors that won't lock. It's an insurance policy built into the structure.
Fair point. That handles the structural part. But we still have to deal with the water.
Always the water.
And this is where the host in me gets frustrated because I see contractors just eyeballing slopes. They kind of wave a hand and say, yeah, it looks like it runs that way. It'll be fine.
And that is where they fail. Eyeballing is not an engineering method. The City of Dallas Drainage Design Manual and the Houston Design Manual don't eyeball anything. They use math.
Of course they do.
Specifically, Manning's equation.
Oh, boy. Math. Give me the equation.
Well, the formula is Q equals V times A. But what it really boils down to are the variables that determine whether your yard floods or not. And those are slope and roughness.
Let's talk slope. Because I have a flat yard. A lot of people do. How much slope do I actually need? Can I even tell?
The absolute minimum for subsurface drains pipes underground is 0.10%, which is almost nothing. But the manuals strongly recommend 1%.
1%. What does that look like?
That's roughly 1/18 of an inch of drop per foot of length.
1/8 of an inch. That's tiny. That's the thickness of a couple of credit cards. That's barely a tilt.
It's not much, but it's critical.
Yeah.
If you are flatter than that, water stands still. And if water stands still in a pipe, what happens?
Stuff settles out.
Sediment settles out, the dirt drops to the bottom, the pipe clogs. Over time, it fills completely with mud.
So the slope isn't just about moving water, it's about keeping the pipe clean.
Yes. It's called self-cleaning velocity. You need the water moving at least 2 feet per second. That creates enough turbulence to scour the pipe and keep the dirt moving out.
Yeah.
If you don't hit that velocity, you are just building a long, skinny, underground septic tank that will eventually fail.
And what about pipe size? I see a lot of those little 4-inch corrugated tubes at the hardware store, the black snake pipes.
Yeah.
I hate those things. But everyone uses them. Are those okay?
For a small downspout, maybe. But if you look at municipal standards, they are much beefier. Residential inlet leads in the public right-of-way often need to be a minimum of 24 inches in diameter.
24 inches, that's a sewer pipe. You could crawl through that.
That's for the main conveyance system. For private connections, they allow 6-inch. But notice they don't say 3-inch or 4-inch. Size matters because of friction and capacity. Small pipes clog easier and have more drag. And here's a detail I loved in the manual that almost no homeowner knows about: the angle of connection.
Oh, right. You can't just T-bone a pipe into another pipe. You can't have a hard right angle.
No 90-degree turns if you can help it. The manual specifies laterals should connect at 60 degrees.
Okay, play devil's advocate here. I'm a contractor. I have a box of 90-degree T-fittings in my truck. They cost $2. The 60-degree fittings are special order. Does that 30-degree difference really matter, or is this engineers just being pedantic?
It matters significantly during peak flow. Think about it like highway traffic. If you are driving on a highway, do you want the on-ramp to merge you in gently? Or do you want a stop sign where you have to cut 90 degrees across traffic doing 70 miles per hour?
I want the merge, a gentle merge.
Right. A 90-degree intersection in a pipe creates massive turbulence. It creates an eddy. It slows down the flow. It causes head loss. That turbulence is where debris drops out and clogs form. You want to merge the water, not crash it.
That makes perfect sense. It's traffic control for water.
Precisely.
Now, everyone loves a French drain. It's the go-to solution for a wet yard. Just dig a trench, throw in some gravel. But the notes imply they're often built wrong.
Often. Almost always. The spacing and depth are key. For a random system in these soils, they recommend 36 inches deep and spaced 50 feet apart. But the big failure point, the thing that kills 90% of French drains, is filtration.
The sock, the fabric that goes around the pipe.
The filter fabric. You must have a filter to prevent soil fines, those tiny clay particles, from washing into the gravel and clogging the system. If you just throw gravel in a ditch with a pipe and no fabric, the clay will migrate into the voids in the gravel.
So mud flows into the rocks.
And in 2 or 3 years, you don't have a French drain. You have a gravel-reinforced clay dam. It stops working completely. You spent all that money and time digging for nothing.
And we are back to the bathtub effect.
Exactly.
This brings us to the final piece of the puzzle, the human factor. Because even if the engineer designs it perfectly, even if we use void forms and 60-degree pipes, we, the homeowners, find creative ways to mess it up.
We are our own worst enemies. Maintenance and aesthetics.
Yeah.
That's where the battle is often lost.
The flower bed dam. I've definitely seen this. I think my neighbor has this.
It's a classic failure mode. You have a foundation. The grading should slope away from it, right, to get water away. That's rule number 1.
Right. Positive drainage.
But the homeowner thinks, I want pretty azaleas right up against the house. I want some height. So they bring in mulch, they bring in garden soil, and they build a berm. A raised bed.
Right against the brick.
Right against the slab. They have effectively built a dam that traps surface water against the foundation. They've reversed the slope.
So rain hits the yard, runs toward the house.
Gets the flower bed berm, stops, and pools. Then it sinks right down the interface between the soil and the foundation. It's a direct injection of water to the place you least want it.
Causing localized swelling.
Exactly. So the foundation lifts right there.
Causing a crack in the drywall inside.
Negative drainage. Created entirely by the desire for pretty flowers.
And then we make it worse with sprinklers.
It's a sprinkler paradox. This is a big one. In expansive soil zones like Texas, irrigation isn't just about keeping plants alive, it's about foundation maintenance.
Explain that, because most people think watering the foundation sounds like a bad idea. You're telling me to water my house?
It's about consistency. Remember, the damage comes from the change, the shrink and the swell. If you let the soil dry out completely, it shrinks away from the foundation. If you keep it wet, it swells. The goal is moisture uniformity. You want the soil to stay at the same volume year-round.
So you're watering the dirt, not the grass. You're trying to keep the moisture levels stable.
Yes. The risk is partial landscaping. Say you water the front yard perfectly because that's where the curb appeal is, but you ignore the backyard because nobody sees it.
The mullet approach to landscaping. Business in front, desert in the back.
Right. So what happens? The front soil stays moist and swells, lifting the front of the house. The back soil shrinks in the summer heat and drops the back of the house.
And the house snaps in the middle.
Exactly. The house breaks. Sprinkler systems in these environments need to wrap all the way around the structure. You need 360-degree moisture control. During droughts, you sometimes even need soaker hoses running constantly just to keep the clay expanded against the concrete.
It's life support for the dirt.
It is. It's a management program.
One last human factor. Trees. We love trees. Shade is crucial. But the report calls them a risk.
Trees are hydraulic pumps. That's the best way to think of them. A large oak tree can transpire hundreds of gallons of water a day.
And it gets that water from the soil.
If that tree is close to the house, it is sucking the moisture out of the clay right under your foundation. That causes localized shrinkage. The house settles near the tree, you get a dip in the foundation.
So cut down all the trees. That seems extreme.
No, but be aware. And keep clearance. The recommendation is at least 6 inches of clearing between the grade and the wall siding to prevent rot and termites. And keep trees far enough away that their drip line isn't over the foundation. Plant the right tree in the right place.
Okay, let's wrap this up. We've unpacked a lot. We've gone from molecular clay lattices to 60-degree pipe angles and cardboard boxes under houses.
That's a lot to take in, I know.
If we have to distill this down for the listener who is just trying to keep their yard from becoming a disaster zone, what are the big takeaways?
Number 1, landscape failure is usually a failure to respect soil physics and chemistry. You cannot fight expansive clay with brute force. You have to accommodate it, like with void forms, or you have to stabilize it chemically, but only after testing for sulfate so you don't blow up your driveway.
Don't create the speed bump. Check.
Number 2, drainage is math, not magic. It's about velocity and slope. If you don't have the slope, that 1%, you don't have drainage, you have storage.
And we do not want to store water under our house.
Never. And so what here? The big picture is that a healthy yard, isn't defined by how green the grass is. It's defined by how well engineered the machine is underneath.
Positive drainage seems to be the mantra. That's the phrase I keep hearing.
It is the single most critical factor in protecting your property value. If water moves away from the structure effectively, 90% of these problems, the heave, the rot, the corrosion, the subsidence, they become manageable.
Now, before we go, I want to get you with a final provocative thought. I was reading through the resilient Houston and green infrastructure sources you included.
Let's hear it.
We spent this whole hour talking about getting water away. Pipe it out, speed it up, get it to the street as fast as possible. But the modern trend in city planning is the opposite. They want us to manage water where it falls.
Right.
Infiltration, rain gardens, permeable pavement.
Right, to prevent flooding downstream. If everyone pipes their water to the river instantly, the river floods. So the idea is to slow it down, let it soak in.
But how do you do that in soil that acts like concrete?
That is the billion-dollar question.
If the soil is black gumbo and holds water like a sealed bowl, how do we use green infrastructure? If I put in a rain garden, am I just building a pond that drowns my foundation by force-feeding that expansive clay?
That is the frontier of landscape engineering right now. How do we make black gumbo act like a sponge without destroying the buildings sitting on top of it? It's going to require new technologies, maybe new soil amendments, or entirely new ways of designing foundations that can tolerate being surrounded by water-holding gardens.
It's a conflict between saving the house and saving the city from floods.
It is. A massive conflict. And the answer isn't simple yet, but it's what we have to figure out next.
Well, on that cheerful note of unresolved engineering challenges, thank you for the deep dive. This has been eye-opening. I'm going to go look at the cracks in my driveway with a whole new level of anxiety.
Happy to help.
To everyone listening, go check your downspouts, check your slopes, and for the love of structural integrity, pull the mulch back from your foundation. Dig deep and keep it dry.
Keep it dry.